Have you ever wondered what's actually happening inside a volcano? We're about to find out. We're going to break down how a seemingly quiet mountain can turn into one of the most powerful forces on Earth, a force that can literally reshape the world around us. So let's dive right in. Okay, let's start with a bit of a riddle. What on earth does a simple can of soda have in common with a massive, erupting volcano? It might sound strange, but I promise you the answer is the key to this entire thing. By the end of this, you'll see how the physics happening right inside this can is a perfect, tiny version of the incredible power building up miles beneath our feet. All right, so to really get what's going on up here on the surface, we have to take a journey deep, deep underground. We're starting at the very source, the planet's inner fire. Now, a lot of people think that this molten rock, which we call magma, comes from the Earth's liquid core. But that's actually a super common misconception. It's really born much higher up, in the upper mantle. Down there, the crazy amount of heat and pressure causes solid rock to partially melt, creating this thick, gooey material that kicks off our whole story. Okay, first things first, let's get a really important definition straight. While all this molten rock is still underground, we call it magma. The absolute instant it breaks through to the surface, it becomes lava. It's the same stuff, just in a different location. And trust me, that distinction is everything. So, we've got our magma. But how does it go from being this relatively calm pool deep underground to, huge eruption? Well, it all comes down to one thing: pressure. And this is where our soda can comes back into play. You see, just like a can of soda is pumped full of dissolved carbon dioxide, magma is absolutely loaded with its own gases, mostly water vapor and CO2. And the only thing keeping those gases trapped is the immense pressure of all the rock sitting on top of it. So here's how it all goes down. First, magma is less dense than the solid rock around it, so it naturally starts to float upward. As it climbs closer to the surface, the weight, the pressure of all that rock above it starts to decrease. That right there is the critical moment. It's exactly like popping the tab on a soda can. Suddenly, the gases can't stay dissolved anymore. They burst out, forming bubbles that expand like crazy, and that just skyrockets the pressure inside the magma chamber. With all of that insane pressure building up from those expanding gases, well, something's gotta give. And that brings us to the main event, the eruption itself. An eruption isn't just one thing. It's this chaotic mix of stuff being thrown out all at once. Of course, you've got the lava, that's the molten rock itself. Then there's something called tephra, which is basically a catch-all term for all the solid bits being blasted out. We're talking everything from superfine ash to boulders the size of a house. And finally, you get that massive release of all the volcanic gases that were powering the whole show to begin with. And if you want to get a sense of the raw energy we're dealing with, just look at this number. The lava flowing from Kilauea in Hawaii erupts at over 2,000 degrees Fahrenheit. Just to put that into perspective for you, that is hot enough to melt solid steel. It is just an incredible amount of heat being unleashed. Now, you've probably seen different kinds of eruptions on TV, right? Some are those relatively gentle, flowing rivers of lava like you see in Hawaii, and then others are just catastrophic explosions like Mount St. Helens. So what makes it one or the other? The entire answer comes down to one single property: viscosity. The easiest way to think about it is just how thick the magma is. Is it thin and runny like water, or is it thick and sticky like, say, peanut butter? Because that one little detail changes absolutely everything. It really is this simple. If the magma has low viscosity, so it's thin and runny, those gas bubbles can escape pretty easily. That gives you those calmer, flowing eruptions. But if it has high viscosity, if it's thick and sticky, it traps those gases. The pressure just builds and builds and builds until you get a violent, explosive eruption. It's literally the difference between bubbles gently rising in a glass of water versus a champagne cork blasting across the room. So these eruptions, they aren't just local events. They are a fundamental force of our planet, and their impacts can be felt all across the globe. The scale of this is truly massive. There are about 1,350 potentially active volcanoes just on land, and that number doesn't even count the thousands more that are hidden under the oceans. These things are geological engines, and they are constantly at work shaping our world. And their power can be genuinely world-changing. I mean, when Mount Pinatubo erupted back in 1991, it shot so much gas and ash high up into the stratosphere that it basically created a sun shield for the whole planet, reflecting sunlight back into space. The result? Global temperatures actually dropped for 2 full years. Just think about that for a second. One single volcano can change the entire planet's climate. And that leads us to one last really big question. We've just seen how these incredible natural forces work. So, in a world that already has a rapidly changing climate, how do you think these massive, unpredictable eruptions might play into our future? I'd love to hear what you think, so drop your thoughts in the comments below. Thanks for joining me.